The idea of resolution is simple. Suppose we know that P is true or Q is true. Suppose we also know that Q is false or R is true. One clause contains Q and the other contains not Q. If Q is false, then by the first clause, P must be true. If Q is true, then by the second clause, R must be true. Since Q must be either true or false, then it must be the case that either P is true or R is true. In other words, we can cancel the Q literals. This intuition is the basis for the rule of inference shown here. Given a clause containing a literal chi and another clause containing the literal not chi, we can infer the clause consisting all of the literals of both clauses without this complementary pair. This rule of inference is called the resolution principle, or alternatively, propositional resolution. The case we just discussed is an example. If we have the clause P or Q, and we also have the clause not Q or R, then we can derive the clause P or R in a single step. The rule is quite simple, but there are some issues to keep in mind, and one common pitfall to avoid. First of all, there's this issue of collapse. Since clauses are sets, there cannot be two occurrences of any literal in a clause. Therefore, in drawing a conclusion from two clauses that share a literal, as in this case, we merge the two occurrences into one, here resulting in a singleton clause Q. Resolving two singleton clauses leads to the empty clause, that is, a clause containing no literals at all. The derivation of the empty clause means that the set of clauses contains a contradiction. If two clauses resolve, they can have more than one resolvent because there can be more than one way in which to choose the literals being canceled. The example shown here illustrates this possibility. We can resolve on P, producing one result, or we can resolve on Q, producing a different result. And here's the pitfall. In resolving two clauses, only where there's more than one possible resolution, only one pair of literals may be resolved at a time, even though there are multiple resolvable pairs. For example, the case shown here is not a legal application of propositional resolution. If we allow this to go through, we would be saying that these two clauses are inconsistent. However, it's perfectly possible for P or Q to be true and not P or Q to be true at the same time. For example, we just let P be true and Q be false, and we've satisfied both clauses. It's noteworthy that resolution subsumes many of our other rules of inference. Consider, for example, implication elimination, shown here on the left. If we have P implies Q, and we have P, then we can deduce Q. The clausal form of the premises and conclusion are shown here on the right. The implication P implies Q corresponds to the clause not P or Q, and P corresponds to the singleton clause P. We have two clauses with a complementary literal, and so we can cancel those complementary literals and derive the clause Q, which is, of course, the clausal form of the atomic sentence Q. As another example, recall the case of formal reasoning introduced in Chapter 1. We said that whenever we have two rules in which the left-hand side of one contains a proposition constant that occurs on the right-hand side of the other, then we can cancel those constants and deduce a new rule by combining the remaining constants on the left-hand sides of both rules and the remaining constants on the right-hand sides of both rules. So it turns out this is just propositional resolution. On the right, here, we have the clausal form of the sentences on the left. In place of the first sentence, we have the clause not P or Q. And in place of the second sentence, we have not M or not R or P or Q. Canceling the P literals, we can deduce not M or not R or Q, which is, of course, the clausal form of the sentence we derived on the left. This exercise tests your understanding of the resolution rule of inference.